Okay, I hope you can see the screen. Wait, uh, is all right. Good. Okay, please fill the form again. Sorry, I've told multiple times, but it's important. Um, so today we are going to talk about quantum algorithms. So as I mentioned earlier, I'll teach some part of this, and then Professor Ram will teach the remaining. So, so the point is that so till now we have been discussing a lot about quantum mechanics and how the transmon based quantum computers work. So now, why are we really interested? Why are millions of dollars being invested in quantum computation? Because it can solve certain, at least that's the hope, or at least that's what, at least theoretically, people have shown that with quantum computation, you can do things that you probably can't do it that fast on a classical computer. Okay, for example, one of the famous problems is the problem of, factoring a number. Okay, let's say you have a large number and you want to find the prime factors of it. Okay, so how do you do that? So there is an algorithm, okay, the classical algorithm, which takes exponential time. Okay, so you can't solve this problem polynomial time if you do it classically. Okay, and why we want to solve this problem? Because this problem has implications in cryptography. Okay, so if you are crypting or decrypting or encrypting your data, if you want to securely send your data, uh, we need so the this prime factoring actually helps us with that. Okay. Another example is the search algorithm. So, for example, if you have 10 boxes and one of them has the price, so the classical way to do it will be, to search one box one at a time, right? And that's going to take you at least 9 steps to, I mean, the worst case scenario. But with quantum, at least the hope is that at one shot you can solve the problem. Okay, if you design a clever enough algorithm, because it'll like simultaneously probe all the quote unquote 9 boxes, 10 boxes. Okay, and then there's something called as quantum Fourier transform, which is used for, which is actually useful in Shor's algorithm. And there are other problems as well. For example, phase estimation, and there's something called as the HHL algorithm, which is an algorithm to solve linear systems. Okay, it's a quantum algorithm to solve linear system of equations, and you can even emulate physical systems. So let's say you want to study some quantum mechanical system, right? So your Hilbert space actually is very large, right? So let's say even if you have 10 particles, my Hilbert space is like 1,000. The dimension is like, if like each particle has 2 degrees of freedom, then my Hilbert space itself is, uh, has 1,000 vectors, right? So you need large computation to, diagonalize such a huge matrix. I mean, 1,000 by 1,000 is still possible, but then the system size increases. Then, of course, the size of the Hilbert space it grows exponentially. But so you can use quantum computation to do this quantum simulation because your stuff already is quantum. Okay, and then there's quantum machine learning, which is also the current frontier. So of course we will not have time to do all of this, but we will try to give some flavor of this in this lecture. So So in classical, if you just compare classical versus quantum information, in classical, you work with either zeros or one. Your bit either is on or off, zero or one. But of course, a quantum bit, because of superposition, it can be in a superposition state, right? And the measurement in classical computation is deterministic. But of course, here it's all based on probabilities. That's why you'll have to do a single shot, again, a single measurement is not going to be enough. You'll have to do an ensemble, take an ensemble and then do the measurement, and then you'll get some statistics out. And then from that statistics, you can infer what your answer is. So just like you have logic gates in classical information, you have unitary gates. And why unitary? Because in quantum mechanics, unitary, we work with unitary transformations, right? So if you want to time evolve the system, it's a unitary evolution. At least if the system is not interacting with the environment, the decoherence is small, then it's a unitary evolution. And so copying is allowed, as you all have seen in classical, but there's this no cloning theorem in quantum, which doesn't allow you to clone information, right? So here and again, for classical computation, your information has one definite value, but here it's like a continuum of amplitude. So these are some key differences between how the classical and quantum computation work, and some of this you have already been familiar with. Now, how does quantum mechanics, at least what's the concept behind quantum computers, why it is so interesting is because of this something called, we can call it as a quantum parallelism. Okay, so let's say you have you have some input x, and you want to find the value f of x, where f is some function. Okay, so what would you ideally do is, let's say you want to f of x, or what's the function, you'll plug in some value of x, and then you'll find the value of f of x, right? For each value of x, you'll have to, let's say, do it. Let's say if you want to do it for 1,000 values of x, you'll have to do it 1,000 times to find f of x, right? But what quantum mechanically, what you could do is you would like prepare it in a superposition state over all these x values. Okay, so taking all these x values, so each x value, for example, could denote a state in your Hilbert space. All right, so this could denote a state 1 in your Hilbert space. This could denote a state 2 in your Hilbert space, and so on and so forth. Okay, so let's say you have all the superposition. Let's say you have n states here. So you create this superposition, right? And then, so this is what is being represented here. Okay, so what we have here, so in one here, this x, this is one state, okay, and f of x is being encoded in the other state. So how this is encoded and all is, we'll see that later, but this is the idea, that you encode x in this state and you encode f of x in this state. Okay, so you have to kind of prepare some sort of a unitary transformation, or some sort of a matrix, a unitary evolution, that if this has x, then this will have f of x. Okay, and then if you can prepare this in a superposition of all the states, okay, and then, so what you do, you prepare this in a superposition, and then if you apply this particular unitary transformation, it is then guaranteed that you will have found all the fx values here. Okay, so all these fx values are like simultaneously copied, okay, quote unquote copied in uh, this particular state vector f. So that's the idea. So we'll see at least one example of how this is done, and then you can use some algorithms to extract the correct answer. So what I'm going to do is I'm going to walk you over quickly with Show's algorithm. Okay, and so that will give you some flavor of how these things could be done, and then Professor Ram will go over the more formal stuff and the Grover's algorithm. Okay, so Show's algorithm is basically the factorization problem that I was mentioning earlier. Okay, so you are given basically some integer n. Okay, typically large integer because well, small integers it's not really that much of a problem anymore because classical computers can do that fast enough. So the question is that how do you find its non-trivial prime factors? Let's say P and Q. We call them by P and Q. So N is P into Q. So classically, you need. It's not a polynomial time algorithm. So you need to do this. You need to wait a lot of time, especially let's say if n is 10 million, for example, okay, or a very large number with 7, 8 digits, it becomes extremely challenging to do it on a classical computer, and the main reason is because you can't do it in a short amount of time. So the algorithm, how it works is, so it reduces this problem of factorization to find the uh, period r of a function. Okay, and for example, to what is this function? So the target is that you have to find the smallest positive r such that a power r is equal to 1 modulus n. Okay, so what does this mean? So let's say you've defined some function f of x is a power x mod n. Okay, so modulus, so this modulus, this is you divide this by this and take the remainder. Okay, that's what the modulus does, right? And this function is actually periodic. So that means after certain interval r, the function basically repeats. Okay, so this r is called as the period of this function. Okay, and then if you let's say you find that r is even and this condition is satisfied, then these two are the non-trivial prime factors of n. Okay, let's see an example. So let's say you have n is equal to 15. Let's say n is equal to 15. Okay, and you choose a as 2. You could choose any a. Only thing that whatever you choose, it should be co-prime with n. Okay, so for example, you cannot choose 3 here. Okay, so let's say, and then this table basically tells you, right? So let's say you put x can take some integer value, let's say 0, 1, 2, 3 and all, and this is a power x and this is a power x modulus 15. Okay, so we see that, so it's like a power x mod 15, it's 1, 2, 4, 8, and then when a power x is 16, right? So 16 divided by 15, the modulus is 1. Right, so the function again repeats. Okay, so that means you have found the period r. So you found the period. So the period here of this function r is actually 4. Okay, and then after that is trivial. You do a power r over 2 and find the greatest common divisor of a power r by 2 minus 1 and comma 15, and a power r by 2 plus 1 comma 15 gives you the prime factors. Okay, you can see another example which is slightly more involved. So this has a longer period. It has a period of 12. Okay, so n is 35. You can pick a as 2, and so the period is 12, and then after you have found the period, then it's very trivial to find the factors, so 7 and 5. in this case. Okay. So what we have done is that, so the problem of factorization, okay, it is basically reduced to the problem of finding a period, finding the period of a function. Okay. And what that function is, well, for this particular case, it is a power x modulus m. Okay. All right. Should A be always 2? No, I don't think A needs to be always 2. So basically, if you see here, if, sorry, let me show you where had I written. Right. So, a suitable integer A co-prime to n. Okay, so A and n have to be co-prime. A needn't be always 2. Okay, that's what you should do. Okay. All right. So this is the factorization problem. Okay, so basically you have to find the period of a function. So that, how do you do that? And there is where your Fourier transforms basically come in. Okay, so we all have seen Fourier transforms in our probably in our college. So discrete Fourier transform is just doing that for a discrete set of variables. So let's say you have some classical data. Let's say you have some class vector, column vector with some data points f0, f1, f2 till fn minus 1. Okay, you can, this is how you can find the discrete Fourier transform. Okay, it's just the same thing that probably you also have seen in your integral version, which you might be more familiar with, right? So it's summation x equal to 0 to n minus 1 f of x and exponential 2 pi I x k divided by. Okay, and this 1 over root n is basically it's the convention. So either you need to put 1 over root n on both when you do Fourier transform or inverse Fourier transform, or you do 1 over n on one of them. But that's the idea of how you do discrete Fourier transform. So we kind of want to do the same thing, but now we are working with quantum bits, right? So let's say you have some Hilbert space and these are your bases. Let's say 0, 1, 2. These are your basis states, okay? Let's say up to q minus 1. So you have total states are q, right? Q states, okay? Okay, so how do you take the Fourier transform? Well, what does, so this is basically, it's the exact same thing that you do for your discrete Fourier transform. Okay, so conceptually it is the same thing. So what you are doing is basically, so you have these states, let's say 0, 1, 2, like that. Okay, and you are doing some, okay, and what is this? This is your basically your quantum Fourier transform matrix. Okay, which is a, which will can show that this is a unitary matrix. Okay, so you here 0 tilde, 1 tilde, 2 tilde are basically the Fourier transform of 0, 1, 2 respectively. Okay, so you can even think, physically, for those of you who are from physics background, when when you change position space to momentum space, right? So that's what you do. It's basically just that, changing one basis to another. So this is some basis, and this is another basis. Okay, this is another basis. Right? Any questions on this? This is basically a quantum Fourier transform, and then you can find what will be the matrix elements of this matrix, and these are just given by these exponentials. Exponential 2 pi I x5 over q with some normalization 1 over square root of q. Okay, and then you can use this particular identity to show that your F is basically a unitary matrix. So that's why this QFT matrix is a unitary matrix. Okay, so this you can do it. It's not it's just a couple of steps in algebra, and then you can prove that F must be a unitary matrix. So let's see an example. For that. So what was our relation? Our relation was that let's say you have some state. How do you do the Fourier transform? Well, summation y is equal to 0 to q minus 1 over root q, exponential 2 pi I xy divided by q, get y. Okay, right. This is the Fourier transform. Now let's do it for a single qubit. So if you have a single qubit, okay, so that means you have just two states, right? 0 and 1. Okay, so these are your two states. So let's say you want to find the Fourier transform of 0. So 0 tilde will going to be 1 over square root 2. And just let's say apply this formula. What do you get? Exponential 2 pi I 0 times 0 by 2 get 0 plus exponential 2 pi I 0 times 1 by 2 get 1, and 1 tilde is the same thing, right? Exponential 2 pi I 1 times 1 by 2. Okay, so these can be easily evaluated. So what is 0 tilde? 0 tilde is 1 over root 2, 0 plus 1, right? And what is 1 tilde? 1 divided by root 2, 0. This is exponential I pi, which is minus 1. So this is my Fourier transform for a single qubit. Okay, this is we call it QFT2. So this underscore 2 means basically it tells you that they are just two states here. Okay, so 0 gets transformed to 0 plus 1, and 1 gets transformed to 0 minus 1. So if you want to write the particular unitary matrix, it's just going to be 1, 1, 1 minus 1. Okay, this is basically, you've seen this gate a lot of time. This is the Hadamard gate. Okay, any questions? Right. So now let's go to multiple qubits. Okay. So you see that in the formula I had something like this, no, x comma x into y. So how do I encode that when I have multiple qubits? So what you can do is you can actually go take the binary. You can go to the binary representation. Okay. So basically, on a real quantum device with n qubits, each integer x is stored in binary. Okay, so all that is telling is basically, so let's say you have two qubits. Okay, if you have two qubits, you have four states, right? What will be the four states? 0, 0, 0, 1, 1, 0, 1, 1. These are your four states, right? So, if you now convert this binary to decimal, what you get? 0, 1, 2, 4, right? this is how you store an integer in binary, no? So I can basically, what I can do is I can denote this cat 00. I can denote it by 0. I can denote cat 01 by this cat 1. I can denote 10 by cat 2. Sorry, this is not 4, this is 3. Right? Any questions on this? This is just straightforward, no? Yeah? Okay, no questions. I hope it's clear. So this is how I do it if I have more than one qubit. So if I have 3 qubits, for example, then I can store the integers up to 0, 1, 2. I can store up to 7. I can store total 8 strings, 8 integers, right? From 0 to 7 with 3 qubits. Yeah? With 4 qubits, I can store from 0 to 15. Okay? Okay, there's absolutely, at least if you can just type a yes or no, then at least I have some feedback that you are following what I'm trying to say. Yes, only 4 people have replied. So, okay. Anyway, in either case, I'll continue. Um, so that's what. So let's see an example for again 2 qubits, right? So let's say I have 2 qubits, 0, 1, 2, 3. Right, and I want to find the Fourier transform. So let's just do for one of them. Let's just do it for example, we can do it for this guy here. Right? So 1 divided by square root of the number of qubits, which is 4. Okay, 0. And exponential will, it's like exponential to 0, which is 1. And an exponential of 2 pi I by 4, which is I pi by 2, 1, right? Plus exponential 2 pi I into 2 by, so this was 1 by, so let's just do it. 2 pi I 1 dot 1 by 4. 2 pi I 1 dot 2 by 4 gets 2 plus exponential 2 pi I 1 dot 3. Okay, so that's how I can actually, now you can generate basically the Fourier transform of, that's how you do the Fourier transform of multiple qubits. So then you can see what will be the corresponding unitary gate. Okay, it will be like half 1, 1, 1, 1, 1 minus I minus 1 minus I, 1 minus 1, 1 minus 1, and 1 minus I minus 1 I. Okay, this is going to be my particular unitary transformation, right? Okay, good. So now let's get back to Shor's algorithm. So what we have done is we have uh, seen the quantum Fourier transform. Okay, and so what we have done so far, that you have your prime factorization. Okay, the problem of prime factorization, that can be reduced to the problem of finding periods of a function, and then you can use the quantum Fourier transform. How to find the period of a function is basically using the quantum Fourier transform. So um, you have a doubt that QFT matrix are we are calculating to make our gates? Yeah, so basically this whole thing, okay, in mathematics, yeah, it's a unitary matrix, but how you implement it, of course, you have to uh, apply certain gates, either single qubit gates or multiple qubit gates, and construct your unitary matrix. Okay, but I think, for example, in Qiskit, there are already some inbuilt functions which implement the QFT for you. Okay, I hope that answers your question. Yeah, okay, good. Um, so yeah, back to Shor's algorithm. So what we want to do is, so you have two systems, X and Y. What X does is X basically stores these integers 0, 1, up to, let's say, q minus 1. Okay, and what y stores the value of the function, let's say a. So if this you call as x, this stores a power x modulus n. Okay, so this is what you have. So, and then what you do, you prepare this system in some uniform superposition. Okay, so for example, your starting state is, let's say, some 0 plus 1 plus 2, okay, q minus 1, and of course, with a normalization, 1 over square root q. This is my state for x, starting state for x. And then so then what I do is I have to implement some sort of a unitary matrix that will store automatically store these in the second. So the second system, the y qubit, will have a power x mod n. A power x mod n. Okay, I will do an example that will make it clear. So this kind of entangles the state. Then what I do is I measure. So I have now my state x and y. Y is a x mod n. Okay. Then I do a measurement on this. Okay, so it is basically it's a superposition. Let's keep that in mind. It's a superposition over all x. Okay, so if I do a measurement on this and I find some answer, okay, so it's basically like this. So if I just try to visualize it, it's let's say if this is my x and let's say this is my f of x. Okay, I'm just trying to do some hand waving kind of argument. So let's say fx, as we have told, is periodic in x. Okay, so let's say it's something like this. Sorry, it repeats after a certain interval. Okay, so this is, let's say, x is 1, x is 2, 3, 4, 1, 2, 3. Oh, sorry, x can take int a lot of values. Let's say 5, 6, 7, 8, 9, 10. But f can take, let's say, f is a periodic function. It can just take certain values. It could be anything. Let's say 2, 4, 6, 8. Okay, I'm just cooking up an example just to show how you can think about this. Okay, so what is happening is that you are creating a superposition state here. Okay, that is in your first. So your first system is in the superposition of all these states. Okay, and then you have implemented a unitary transformation uh, that has f of x, the corresponding f of x on the second system. Okay. Okay, what is basically in your in your quantum computer? This is just some set of qubits, no? This is some set of qubits. This is also some set of qubits, right? So for example, you want to store 0, 1, 2 up to 15, right? You just, let's say x can only take up to from 0 to 15, then you just need 4 qubits. And correspondingly, you have to find what all values f of x can take, and then accordingly, you will have to choose your number of qubits. Okay? So let's say this is my x, the values x can take, and values f of x can take. Okay? And my initial system is in a superposition of all these dots. So all these dots you can think of as like some states in the Hilbert space. And now I measure the system y. Okay, so I'm doing the measurement on this second system, which has encoded f of x. Okay, so again in the Copenhagen way of calling it, the system x then collapses. So let's say I measure 4 here. Okay, this is 4 to 8. Let's say I measure this system, and let's say I get an output 4. So what it tells me that now my state of x will be this, right? What will be my state of x? It will be, let's say, ket2 plus ket6 plus ket10, right? Make sense? Can you please type in the chat box if it makes sense or not? So only 5 answers. So that means out of 19 participants, uh, only 5 are probably paying attention. A bit of a disappointment, but it's okay. Okay. Anyway, I'll just go on. So now my system 1 is in this particular superposition. All right. So now you see that this particular superposition, it has in it hidden the period. The period is actually hidden in this. Right. So now what I will do is to find the period, I can then apply a quantum Fourier transform on this. Okay, so what we do is we measure the system y, we obtain some value of f of x naught. Then in the Copenhagen term, the system x collapses to something, and then we apply the Fourier transform on this state. Okay, this is the x state. Okay, after measurement of y, right? And then from here we can extract the period of the function. Okay, so that's basically how the algorithm works. Okay, so let's take an example that will make this a bit clear. So you start with some initial state 0, 1. 0 is for the x and 1 is for your y. And then you prepare a superposition of all the states in x. Okay, and then you prepare a superposition of all the x states, and then you implement this how to encode f of x in the second qubit. Okay, so now your second qubit it has the function f of x inside it. Okay, and now you do a measurement on the second system, which is this y. And let's say you could measure anything. That's what I was trying to show you. You would probably measure one of these outputs, right? So it has only 4 possible outputs. You'll measure one of these. So if you measure one of these, then your system X will be in this particular superposition. Okay, and then if you apply a quantum Fourier transform, okay, now what you will do is you will apply a Fourier transform on X, and then you will see that, and then you will make the measurement on Y. So what you're doing is, if I just go over it from the starting, you're preparing a superposition of X. Okay, first step, second step, you have X and f of X. Okay, and then you are measuring f of x. Now we know that f of x is periodic. So now my state x has that period information hidden in that. And then what I do is I apply quantum Fourier transform on x. Then I measure x. Okay. And from here I can then back calculate the probability. Okay. So for example, we took this example of the same 2 mod x, 2 power x mod 15, right? This was our f of x. And let's say you measure y is 1. So if you remember my 2 power x mod 15, it could take values 1, 2, 4, 8, 1, 2, 4, 8. So if you measure 1, that means my x will be in a superposition of 0 plus 4 plus 8 plus 12, because that's the time when f of x is going to be 1. Okay, so let's say you measure 1, you could have measured anything else, doesn't matter. Whatever you measure, the information is going to be there. So if I measure 1, for instance, my state is going to be 0 plus 4 plus 8 plus 12. Okay, then I apply a Fourier transform on that, and then I do the measurement. Okay, and then you will get the maximum probabilities only for these four outcomes: 0 or 4 or 8 or 12, and each has probability 1 of or 4. Okay, so you will not obviously implement this in a single shot. You will have to do multiple of these measurements and take the statistics, and then see that which of the values will get some histogram like this, right? And which of the values have a higher probability. And from there, you can infer the period R. And after you get the period R of the function, well, then the rest of it is straightforward. Okay, so this was one very simple example to show how you can use the power of quantum superposition to, let's say, design an algorithm to solve things faster than what you would do on a classical computer. Okay, so this was basically shows algorithm, and so this now will be put in a more formal setting that will be done by Professor Ram in the after this. But I would like to pause here and ask if there are any questions on the Shor's algorithm. Right. Yes, so this runs in polynomial time. Yes, yes. So there is a first, that's right. Exponential speed up. I don't know if it will still be an exponential speed up, because again, you will not be able to conclude anything with just a single measurement. You'll have to do multiple of these. Um, but at least the claim is that it's going to be definitely faster than in the classical. Okay. I mean, if you just think about it, let's say you have, I mean, right now, Your IBM queue has how many? 157 or something qubits, right? And if you with just 20 qubits, right, you can store a very large number with just 20 qubits. Okay, if you have just 10 qubits, right, with 10 qubits, you can encode from 0, 1 up to 1023, right? So, and so with 11 qubits, it goes up to 2047 and so on. So it just very exponentially it increases. So the only thing is like how many qubits you can use, and then there are other factors that come in. That is your state preparation. How good is it? How good are your statistics? And those kind of things. But so yeah, I mean, it has potential, but then again, how much of it is practically possible is another question. Okay, any other questions on Shor's algorithm? Yeah, of course. I mean, it's not supposed to be a very detailed lecture anyway. I've just given you a very kind of a bird's eye view. So you need to, of course, go back and think, and now you can use Qiskit, IBM Qiskit to play with it and do some more things. Okay. Sorry. So the code is also pasted here on the chat box. Okay, so this basically is the code. So you all can run the code and see how it works. Okay. So what we'll do, I think, because it's almost 4 o'clock, so we can stop here and we'll start the next lecture a bit early. We'll start at 4:30. But again, I want to remind everyone to please fill up the feedback form. Okay, who have not filled. Okay, so please do that. And you can use the break time to fill the form and send us. So we'll stop here because um, yeah, so that and we'll start at 4:30, and from 4:30 we'll have the last lecture, and that's about some more on quantum algorithms. Okay.